Hello everyone and welcome to our presentation for the 2022 edition of the EnergyInformatics.Academy conference. My name is Pedro Batista and I guess it's also relevant to share that I'm a software engineer. In the past few years, I was involved in DevOps and software architecture projects for the automotive industry. Today, we will share the main topics about our process of designing a data management service platform for our intelligent electric vehicle controller. In this specific case, for the multi-charger model. It's easier to understand our background and motivations with this overview. As automotive and electric vehicle enthusiasts, we started by first learn about EV charging, the types of electric vehicles, electric vehicle chargers, charger types, charging specs, basically focusing on the chargers. The limitations of domestic charger solutions back in the days and the lack of affordable yet customizable chargers led us to the next stage, where we got involved in this single charger solution. So we built our own charger, which is powered by our own intelligent electric vehicle charging controller. And this charger allows us multiple configurations based on time and charging load. It also saves data locally for further analysis. One of the main features related to this charger is the ability to prevent main switchboard tripping by current limit violation. This means we no longer suffer from power interruptions because of someone suddenly switch on one or more devices at home while we charge our EV, and we call this the dynamic charging. The next stage came naturally to solve the problem of so many electric vehicle enthusiasts. To own an electric vehicle, we not only need to buy the vehicle, but there are some other requirements to meet. For instance, we may, and maybe the most important, we may have the electric vehicle, but we still need to find a place to charge its batteries. And for many families, at least in Portugal, that live in apartments with shared garages, this is definitely a blocker. There are no independent connections for each user to charge his car, and that's why the single charger model evolved. And we started developing a multi-charger solution that could solve this problem. While in the process of building the multi-charger solution of the intelligent charger, and I'll get into more detail about this in a minute, we ended up with this need to handle significant amount of data generated. So, of course, because there isn't much tolerance when dealing with this sensitive data, we needed a resilient and scalable architecture to support one solution that could grow significantly, at least from our perspective. The first developed model was the one with a single charger. Designed to solve some of the use cases for electric vehicle users, the most important from our point of view was the ability the system offered to balance the EV charging load charge. This happens before any power overload tripping is triggered. While executing, all this generated data is stored locally, and then it's available to be fetched by the user so we can check the stats and configure the charger accordingly. The MQTT was the choice for the messaging protocol. It has its proven value in the IoT world and offers the security options we needed for our solution, like password authentication and certificates. The evolution of the previous diagram is the multi-charger model. Although the concept for a single charger remains similar, there are much more challenges to tackle within this scenario. Each client needs to be authorized to connect to the network. The energy load balance needs to consider every device, and multiple mechanisms of prioritization can be configured. As described in our motivation slide, soon we identified multiple challenges while designing this model. The broker response time needs to be fast enough to act before any power overload is tripped, and this means that due to device CPU restrictions, it's not possible to rely on these devices to handle all the processing for the generated data. And that was when we understood that multiple powerful machines were needed, and it would be more expensive to include these in the local setup. We consider that our solution matches the pattern of a streaming analytics system. This pattern usually consists of three layers: ingestion, processing, and storage. Based on this, and trying to port it to fit an IoT data processing architecture, our research concluded that the best fit would be the association of fog-based and cloud-based processing. Cloud computing and fog computing infrastructures do not compete with each other. They're complementary in this case. The IoT applications connect across fog nodes, and devices must be connected to at least one of these fog nodes represented in this gray area. Any device part of the device layer of our solution may connect to fog nodes, which may be used in specific geographical cloud areas. Because each fog node is a single point of failure, its spread and replication across regions should be considered for failure, recovery, and redundancy. The device layer will include all the devices that support our solution locally, and it will include everything related to network, but of course the smart ESP32 based devices, currently the chargers and electricity meters, but can be any other thing. Multiple other IoT devices can be integrated in the future. The fog layer will include the devices capable of processing and handle the generated data in an intermediate stage. And by splitting this processing power across multiple regions, it will decrease the total load each fog node will handle, while it increases redundancy, and of course this is a significant concern when we deal with critical data. The cloud layer will ensure everything the cloud computing infrastructure stands for. So it will give us the reliability when we want to make sure our persistent data will be there when we need it. With our multi-charger solution architecture in place, we were finally prepared to work on the tech stack. So we're ready to share our results. But first, it's important to share the tech stack definition. So a tech stack consists of the choice of the technologies to develop and manage an application or project. Usually, it includes programming languages, frameworks, databases, front-end and back-end tools, and applications linked through one or multiple APIs. If we start our analysis from top to bottom, this device layer includes the local devices and the device applications. Currently, our solution applications are heavily based on C++ and Python and are represented by this entity here. And we also included a time series database, which is InfluxDB instance that will store and forward data to the fog layer. In the fog layer, which it's where the Apache Kafka instances will be working on, these multiple instances will be replicated, and of course will give us the response time, because they will be close enough to our device layer to ensure that the response times will be fast enough. And we can not only store the data we need, we can also start doing some processing and cleansing on top of this data, the collected data. So then we can forward it to our cloud layer, where time is not that critical anymore. So we can do whatever data processing we intend to, and then we can store it in our Postgres database cluster. Concluding, when collecting and analyzing high loads of information, it's important to be able to do so in a way that works efficiently at different stages. Regardless of the ease of adopting one software stack component over another, it's difficult to articulate how each layer interacts. Also, benchmarks are crucial when layer responsibility is determined. Software engineering is crucial in ensuring that entities in each layer make the most use of the underlying layer resources. Finally, I would like to share a brief info about myself and share my contacts, so feel free to reach out, and I'm now open to any questions.